Get started. Yeah, cool. So today, we are going to understand probability in mathematics, and that is the main learning objective. Probability is a branch of mathematics that measures the likelihood of events occurring. It assigns a value between 0 and 1 or 0% and 100% to represent how likely an event is to happen. A probability of 0 means that the event is impossible, while a probability of 1 means that it is certain. In computing, probability is used in areas such as data science, machine learning, cybersecurity, game design, simulation modeling, and artificial intelligence. Understanding probability allows developers, analysts, and engineers to make predictions, assess risk, optimize performance, and build intelligent systems. So, just to go through that here. Sorry. So an experiment is an action with uncertain outcomes, for example, tossing a coin or selecting a file at random. Sample space, the set of the set of the set of all possible outcomes. For example, for a coin toss, S could equals heads or tails. Event, a specific outcome or a set of outcomes that from the sample space. For example, E getting heads, that could happen. Probability formula P brackets E equals number of favorable outcomes, total number of outcomes, divided by total number of outcomes, sorry. So for example, rolling a four on a fair dice, P4 equals 16. Oh, sorry, that is the total number, the, the number of favorable outcomes. Yeah. So that is 16. So the types of probability I explained here, theoretical probability, as spoken about before, based on unknown possible outcomes. Experimental probability based on actual experiment results or simulations. Subjective probability based on personal judgment or estimation. And an example of the first one is predicting file collision in hashing. Second one is analyzing logging failures over time. And the last one is assessing risk of system breach based on previous incidents. Application of probability in computing. Algorithms use probability to classify data, predict outcomes, and determine confidence levels. Naive Bayes classifiers use probabilities to sort emails into spam and non-spam. Cybersecurity risk assessment models use probability to determine the likelihood of data breaches or system failures. Probabilistic password strength assessments help prevent weak login credentials. Game development, probability controls events such as item drops, enemy spawns, and dice rolls in games. Network and system reliability, predicting the probability of server downtime or hardware failure used in queuing theory or persistent performance modeling. And finally, search engines and recommendation systems. Google's PageRank algorithm is based on probability. Recommendation engines use probabilistic filtering to suggest content. For example, a single event, probability of drawing an ace from a deck, P ace equals 452. Equals 1. That's the probability of drawing an ace. P not A equals 1 minus PA. Example, if PA is 0.75, then P not A would be 0.25. Compound events and independent events P and A and B equals PA times PB, or mutually exclusive events PA mutually exclusive B equals PA plus PB. Example, probability of rolling a 2 or 4 on a fair die. P2 union 4 equals 16 plus 16, which equals 32, it should say there, not 26. I don't know why it says that. Yeah, so summary table probability in computing. So I've spoken about before this has the concept, the explanation, and the example in computing. And I'll give you a couple of minutes to have a look at this and then we will move on from here. Mhm. Well, guys, we'll move on now. So that's okay. Should we move on? Yeah. So the conclusion here is that understanding probability in mathematics equips computing professionals with the tools needed to assess uncertainty, model risk, and make data-driven decisions. Whether predicting server crashes, detecting threats, or training AI models, probability enables smarter, more informed computing systems. It bridges the gap between theoretical analysis and real-world applications, making it an essential area of study in computing. Probability theory is the branch of mathematics concerned with analyzing random phenomena. It provides a framework for predicting the likelihood of different outcomes in uncertain situations. In computing, probability theory is essential for managing risk, building predictive models, simulating systems, and supporting decision making. Definition of probability. Probability is the measure of how likely an event is to occur, expressed as a number between 0 and 1, or as a percentage between 0% and 100%. Probability of 0 means that the event is impossible. Probability of 1 means that event is certain. And a probability of 0.5 means that there is an equal chance of occurrence or non-occurrence. The fundamental formula for calculating the probability of a single event is PE equals number of favorable outcomes divided by total number of outcomes. The probability of rolling a 6 on a six-sided dice is P6, which equals 16. Sorry, give me 1 second, guys. 1 second. Oh, sorry. Just to confirm to you guys what this means here, it's not actually 16, it's just um It's just the way it's written, it should actually be 1/6. So it's the total number of outcomes, which is one of getting a six over the I mean, it's the number of favorable outcomes, which is one, because you can only get six once on a six-sided die, and the total number of outcomes is six, because you can get any of the six numbers, so it's 1/6. Key probability concept experiment. The concept of experiment is a process that leads to one or several possible outcomes. For example, tossing a coin. The concept of sample space is the set of all possible outcomes. For example, for a die roll, it would be 1, 2, 3, 4, 5, and 6. Event is a subset of a sample space, for i.e., one or more outcomes rolling an even number on a die. The event that complement is the event that E does not occur, so I'm not rolling a six. Mutually exclusive is events that cannot happen at the same time. For example, rolling a two and a three on a one die roll. Independent events are events where the outcome of one does not affect the outcome of another. For example, two coin tosses. Theoretical probability is calculated using known possible outcomes under ideal conditions. For example, PE equals favorable outcomes over the total number of outcomes. An example of this is probability of drawing a heart from a full deck of 52 cards. P heart equals 13/52, which equals 1/4. So based on actual data from experiments or observations. This is experimental probability. P equals number of times E occurred divided by number of trials. For example, if fire load fails 20 times out of 100, then P failure equals 20/100, which equals 0.2. Subjective probability is an estimated probability based on intuition or past experience without exact data. Example here is a network engineer estimates 70% chance of a cyber attack based on recent patterns. 5 compound events. Addition rule for all events. If A and B are mutually exclusive, PA and BA union B equals PA plus BB. Multiplication rules. If A and B are independent, PA and B equals PA times PB. For example, probability of flipping two heads, H and H equals 1/2 times 1/2, which equals 1/4. So that is the answer. Application of probability in computing, the area of machine learning. The use of probability here to predict classifications and confidence levels. Cybersecurity, risk modeling, and threat prediction are the used here. In search algorithms, PageRank uses probability to rank web pages, and in game development, random number generation, item drops, and character behavior. Simulation and modeling in this running stochastic randomized simulation, and in networking, estimating data packet loss or transmission error rates. Python example, simulate coin tosses. Here's a piece of code in Python. So defining the function of toss coin equals return heads if random.random is less than 0.5, else return tails. Results equals total cost for in range of 1,000. Probability of head equals results dot count heads over 1,000, and then print this number as the probability of heads. Here's a summary table of probability theory concepts. So first, probability, the likelihood of an event happening. That's the meaning of it. And an example is P rain equals zero point 0.3 sample space. The meaning of this is that all possible outcomes. And an example of this is S equals 1, 2, 3, 4, 5, 6 on the dice. Event is a particular outcome of a set of outcomes. For example, rolling an odd number on a die. Independent events, outcomes that do not affect each other. And this, for example, there's two dice rolls, mutually exclusive events that cannot happen at the same time. For example, drawing an ace or a king on a card. An experimental probability is based on trials or observations. So, for example, 75 login successes out of 100. The conclusion here is that probability theory is a fundamental mathematical framework used in computing to quantify uncertainty, assess risk, and model real-world behavior. Whether in machine learning, gaming, cybersecurity, or decision making, understanding probability enables developers and analysts to make accurate predictions, automate intelligent systems, and improve performance outcomes. Complement rule is used to calculate the probability of an event that is not happening. For example, P not A is 1 minus PA. An example in computing is that if the probability of a server being online is 0.98, probability of it being offline is 1 minus 0.98, which equals 0.02. Addition rules. So for all events, for mutually exclusive events, A or B equals PA plus BB. For example, in a search engine, if the probability of a user clicking on ad A is 0.3 and ad B is 0.2, then they are not shown together. P click A or B equals 0.3 plus 0.2, which equals 0.5. For non-mutually exclusive events, PA and B, PA or B, PA plus PB plus PB, take away PA and B. For example, if 30% of users visit a page and 20% click on an ad and 10 do both, page widget or ad click equals 0.3 plus 0.2 minus 0.1, which equals 0.4. The multiplication rules for independent event PA and B equals PA times PB. For example, the chance of two independent sensors failing is PS1 and S2, each equals 0.05 times 0.02, which equals 0.001, or 0.1%. For dependent events, PA and B equals PA times PBA, where PBA is the conditional probability of B given that A has occurred. PB given that A has occurred equals PA and B multiplied by PA. No, yeah, no, yeah, multiplied by PA, multiplied by PA given all B. So an example in computing is that if 60% of users use the mobile app, and 40% of them also use the web version, PB PBA equals 0.4, which means that PA and B equals 0.6 times 0.4, which equals 0.24. 0.24. Therefore, 20% of all users use both platforms. Bayes' theorem. Using machine learning, spam filters, and predictive modeling. PAAB equals PBA .PAPB. An example in computing is used in naive Bayes classifiers to estimate the probability that a message is spun based on the words it contains. Below are the real-world computing applications. There's the formula, what it's used for, an example in computing. You can have a look at that for a few minutes and then we'll move on.
Yeah, you can. I'm continue.
All that. So summary table again. I think this is just showing the formulas and what is used in again. Um, so I'll give you a minute or so to have a look at the formulas of each of these. We will move on if that's okay with you.
Yeah,
So the conclusion is that understanding probability formulas is crucial in computing as they allow professionals to model uncertainty, evaluate risks, and optimize systems from conditional logic in software to machine learning classifiers and system reliability. These formulas empower data-driven decision making and intelligent automation. Mastery of these principles is fundamental to modern computing, especially in data analysis, AI, and cybersecurity. In probability theory, calculating the likelihood of an event occurring involves applying a suitable formula based on the nature of the event, for example, single, compound, or conditional. In computing, this is often used to estimate outcomes like system reliability, algorithm success rates, and user behaviors in various applications. For example, basic probability formula, probability PE of an event EE occurring is calculated as PE equal number of favorable outcomes divided by total number of possible outcomes. Scenario here is a cybersecurity analyst is assessing the probability that a user will log in successfully on the first attempt. From past data, it's known that 700 out of 1,000 login attempts are successful. Step-by-step calculation here is that for step one, you identify the sample space. The total attempts equals 1,000. Step two, identify the favorable outcomes. Successful logins were 700. And then step three, apply the formula. For example, P successful login equals 700 divided by 1,000, which equals 0.7. So the probability of a successful login on the first attempt is 0.7, otherwise known as 70%. In- Interpretation. This means that based on its historical data, there is a 70% chance that any given user will successfully log in on their first try. The remaining 30% might forget their password, enter wrong credentials, or face technical issues. This insight can help system designers to simplify login procedures, security teams to detect anomalies, for example, multiple failed attempts, UX teams to improve user interface and user experience. Additional example, probability of server crash. A server has a known crash rate of 2% per day. P server crash equals 0.02. So therefore, P no crash equals mod minus 0.02, which equals 0.98. Therefore, the server has a 98% chance of running without crashing on any given day. Visualizing probabilities with the table. So it shows here how to visualize probabilities with the table, for example. As we discussed, successful login, the favorable outcome was 700 out of the total outcome of 1,000, therefore the probability is 0.7. Consequently, opposite fail of successful login is failed login. So 1,000 minus, I mean, 1,000 minus 700 equals 300, which is the favorable outcomes out of 1,000 again. This means the probability is 0.3. So the crash is 2 out of 100 favorable outcomes, and the probability is 0.02. And server running is 98 out of 100, therefore the probability is 0.98. Application in computing fields, cybersecurity estimates chances of breaching, password failure rates. Machine learning predicts classification accuracy and error rates. Networking calculates packet loss or connection success. Cloud computing models uptime and availability, for example, 99.9% reliability. And game development determines event likelihood, like winning or item drops. The conclusion here is that calculating the probability of an event is essential in computing to evaluate performance, reliability, and user behavior, whether assessing logging success, server uptime, or system failure. Probability allows professionals to make informed decisions and optimize systems. Understanding and applying basic probability calculation helps create more robust and data-driven technologies. The references today's are the following books, which would be quite useful for you guys in your further reading for your assessment. And as usual, it's good to do further reading. Refer to the ebooks and journals on Moodle. And if you have any queries and questions, please ask me now or ask me later on in the group chat. Alternatively, you can kindly email the following email. And submission of the assignment is to be done and submitted to the following email as well. And the assignment submission is 2 weeks after the completion of the units and its delivery. So cool. Today was a shorter lesson. I believe tomorrow will be a longer one, so we'll make up for it. But if you guys have any questions, let me know. Otherwise, you guys are free to go today.
Yeah, thank you.
I think Shima has disconnected. But yeah, that's cool, mate. Nice one, Clement. You can go.
Okay, thank you.
Thank you. Bye.
Bye.